All right, so what are the different shapes that take place, or that make up Richard Pryor on the Wonder Wheel? If I go back to this table, what are the different shapes that I can use to make up that Wonder Wheel? There are two shapes. What's the first one? It's a hoop, right? It's a big hoop. It has a certain radius. We can estimate what that radius is, and then it also has a mass. So we'll estimate the mass. It's a couple kilograms. It's not that big. All right, so the hoop is one thing. And then what's the other thing? What's that? What do y'all think? The cylinder. Okay, it's one of the cylinders. Is it this cylinder? No, because we're not spinning about this axis. Instead, he's spinning about this axis. So we have two parts. We have the hoop, or the wheel, and then we also have the cylinder. So we need to look at both of those, and we'll add them up. I forgot my notes today, people, so I'm sort of winging it. I might have to go back or ask you. It's on the previous page. So we're going to treat the system as a hoop and a cylinder with the axis of rotation through the middle. I'll draw a picture. So we're going to have our hoop. It'll have a certain mass. Let's say that the mass, we'll say that it's 10 kilograms. And then that its radius is, I don't know, 2 meters. It might be a little shorter, or a little bigger than 2 meters, but let's just say that it's 2 meters. And then we also have Richard Pryor with very long legs in the middle there. But we can approximate Richard Pryor as a cylinder, and we'll do that. Approximate him as a cylinder. And we'll say that that cylinder has a radius equal to, well, this distance, which is, I don't know, 20 or 30 centimeters. Let's just call it 20 centimeters. That's 0.2 meters. And then it has a mass, just to make the numbers easy, we'll say 100 kilograms. So 100 kilograms, it's a pretty big guy, 100 kilograms. So he's probably not Richard Pryor. Okay? So now we would calculate Richard Pryor's moment of inertia. It's going to be, the total moment of inertia will be the moment of inertia of a hoop plus the moment of inertia of a cylinder. But we got to watch what axis we use and which of those. Remember, there are two. So that's going to be the mass of the hoop times the radius of the hoop squared plus, I'm going to need to go back up. I'm sorry, I don't remember what that was. Quarter mr squared plus a 12th mv squared. And that's the mass of Richard Pryor, the radius of Richard Pryor, and the length of Richard Pryor. Not Richard Young, Richard Pryor. You get the idea. All right? And so now that we have that, we would add those two together to figure out what is our total moment of inertia. I'll put in the numbers, but I'm not going to calculate it. It's going to be the mass of the hoop, which we said was 10 kilograms. The radius of the hoop, well, I said it was 2 meters. Actually, the diameter is 2 meters. We'll say that the radius is 1 meter. I'm getting that because Richard Pryor is about 6 foot tall, and so the hoop is about that height as well. So the radius of the hoop, we'll say, is 1 meter squared plus a quarter of 100 times 1 meter. I'm going to go back to that figure, okay? We got to be careful with what we're doing here. I'm sorry, that was the radius, B. Yeah, like I'm not being careful. The radius, we said, was 0.2 meters. Plus 1/12 the mass, which is 100 kilograms, times the length of the cylinder, which is going to be 2 meters squared. So that's how we would find the moment of inertia of this system, which consists of two different parts. You'll almost certainly have to do this on the exam, where I give you a system that has one or more parts, and we'll do some examples. Usually it's two spinning parts that come together, and then you have to know their total moment of inertia. But in this case, it was two parts that were spinning together, and you needed to know their moment of inertia. Okay? And this is whatever it is. I'm not sure what the value is. All right, let's try this one. Here you have these four balls, each is 1 kilogram, and they're connected by 1 meter rods. And I want to know what is the moment of inertia of that configuration. Whenever you encounter these questions, first you want to ask yourself, okay, is this a collection of particles, or is this one of those rigid shapes that I have the table for? If it's particles, then you do the sum of mr squared. If it's one of those shapes from the table, then you need to pick out which is the right shape from that table. So first ask yourself that question, which is this? A collection of particles, or is it one of those rigid shapes? All right, let's do about 10 more seconds. We'll go to 220. 220? Let's guess if you're not sure. Okay, yeah, I think D is right. So first of all, is this a rigid shape or is this a collection of particles? It's a collection of particles. So to find this, I would say I is equal to the sum of mr squared. And I know that this distance is 1 meter, but I'm rotating about this axis. So this distance is a half a meter. It bisects that. And so I know that each of these is 1 kilogram. For each individual particle, the moment of inertia is going to be m, that's 1 kilogram, times 0.5 meters squared, plus 1 kilogram times 0.5 meters squared, plus 1 kilogram times 0.5 meters squared, on and on. There are 4 of these, so I just multiply times 4. They're all identical, so I can just multiply by 4. If they weren't identical, then I would just add up those individual terms. So that's equal to 1. And then the units for this are kilogram meter squared. Nothing fancy, no new units. We're just doing kilogram meter squared. Okay? You'll likely have a problem where I just ask you, what is the moment of inertia of this object? And it'll either be a collection of particles or a rigid shape, or it might be 2 rigid shapes smashed together, and you have to figure out what is the moment of inertia. Let me just point out some things that sometimes trip students up on this. And it tripped me up too, right? The one thing is that you need to make sure that you're dealing with the radius and the lengths on these cylinders, that you get that straight. Is this the radius that I'm asking, which is this distance, or the length, which is the distance from head to foot, when we're dealing with Richard Pryor? So that's one thing. The other thing is that so often I'll give you a spinning disc, And a spinning disk is the same as a cylinder. We'll see it again soon. But if you ever see a spinning disk, that is a disk that's rotating about that axis, then that's the same as a cylinder. It's just a flat cylinder, right? So for example, a spinning disk, I often like to do a merry-go-round problem. A spinning disk is a merry-go-round, or rather a merry-go-round is a spinning disk, which is a cylinder. All right? That sometimes trips students up. All right, so we saw Newton's second law before with the force is equal to ma. And remember, we've been making these changes from the linear system to the rotational system. That is, where we had x, we now have theta. Where we have v, we now have omega. Where we had a, we now had alpha. And you'll see these again on this test. I know that we saw it on the last test, but we'll see it again with Chapter 8. Where we had, what else did we have? Where we had force before, we now have torques, which remember I described those sort of as like an angular force. It's not really correct, but it's a force times the moment arm. And now where we have mass, we now have moment of inertia. So if we were to rewrite Newton's second law, think about what it would look like. That I would take these variables, F equals ma, and replace them with our new angular quantities. Newton's second law also applies in circular motion. I'm sorry, I don't have my notes today. I forgot them. So I'm forgetting what goes in these blanks. Do y'all have any ideas? You know? What is it? Okay, moment of inertia and the acceleration. The moment of inertia is a measure of the object's inertia. Okay, object's rotational inertia, thank you. Acceleration? Okay, and the angular acceleration is a measure of the rotational acceleration. That is, say that if I were to rewrite this, I would have that my torque is equal to that moment of inertia, which is kind of like our mass, it's a lot like our mass, times our angular acceleration, which is alpha, my angular acceleration. Okay? Just like we had before when we were dealing in Chapter 7, torques in the clockwise direction are considered to be negative, and those in the counterclockwise direction are considered to be positive. All right, so we'll have to consider that as well. I think we've already actually seen that, where we added up torques. All right, we found out what is the net torque on an object. Let's not do this example right now. Let's go and do a few clicker questions from the back. I think we left off on this one, right? All right, let's stop at 55. 55. Okay, good. B is right. The hollow goal. Remember that our moment of inertia, we can think about this just in terms of the definition of moment of inertia, that I is equal to the sum of mr squared. So if I put a lot of mass out at big radii, then that means I'm going to have a bigger moment of inertia. So this one has a bigger moment of inertia just because it has a lot of mass at big radii. And because of that, it makes it harder to spin. Okay? They have the same mass, but because this one's hollow, it has more mass at larger radii. Okay? If you forget that, you can look at your table, and you see that one is 2/3 mr squared and one is 2/5 mr squared. And then you say, well, which fraction is bigger, 2/3 or 2/5? I think that's what it was. Okay? Let's see. See, the thing is, folks, can I tell you a secret? I know that you're going to be disappointed. Is that, like, all those jokes that I tell you, I have a piece of paper up here that's in my notebook. Because otherwise I'd just be telling you the same jokes over and over, but I don't remember which ones I tell you. So y'all might have heard this one. Have y'all heard the O Street one? You haven't heard that one? Oh, good. Okay. So what's the worst thing about living on O Street?
Yeah, we heard this one.
Oh, okay. You have to walk a whole block. Does that one count? Can we just let that one count? Because y'all have forgotten it. Okay. Are y'all disappointed? Like, you thought that I just knew all those jokes off the top of my head. I do know them. It's just I can't keep track of which ones I've told you. Okay. There we go. So it's the hollow gold. Oh, I like this problem. You make 4 T's out of 2 identical rods of equal mass. So you have 2 bars that are exactly the same length and mass, and then you put them together in different ways. Which of these, or rank these from the biggest to the smallest moment of inertia? Biggest to smallest. The one with the biggest moment of inertia will have the most mass at large radii. The one with the smallest moment of inertia will have the least mass at large radii, or more mass at small radii. Alrighty, let's stop at 118. 118. Okay, so D is right, I think. The way you want to approach these, and in general for ranking problems, which not only do I like them, but other people like them too, on these various standardized tests that you folks take, try to eliminate options first. And so a good way to eliminate options is say, well, which one of these has the biggest moment? Well, this one right here has this bar out at the maximum radius it can get to be, right? Because it's at this length. And so this one has to have the biggest moment of inertia compared to all these others. So I could get rid of then A and B. It's either going to be C, D, or E. And then ask myself, which one has the smallest moment of inertia? Well, which one has, it's either going to be this one or this one, because they have a whole bar that's at R equals 0, at 0 radius. So in fact, this bar is not going to contribute to the moment of inertia at all. And so which one of these is bigger, or which one is smaller, rather? Well, C is smaller, right, because I have mass out at R over 2, but here I have mass out at R. So I have more mass at larger radii here. So the biggest one is A, and the smallest one is C. So then I can get rid of all 3 of those. And now I need to ask myself, which is D or B is bigger? Well, D is going to be, D is going to be bigger. Did we mark D as the answer? Yeah, okay, good. Yeah, D is the bigger one. Because if you think about this, if I were to take this rod away, this system would be identical to this system. Let me repeat that. If I take this bar, the one that's sticking up, this bar rotating about this axis is identical to this bar rotating about this axis. Those would be the same. And then I'm just adding on this extra bar. All right, so this one has a bigger moment of inertia. D is bigger than D, so D then is the right answer. You want to go through that process. You'll see at least one ranking problem on this test. We've seen some others with torques, probably two maybe. I like them, not because they help you to understand moments of inertia or they assess whether you understand moments of inertia, but it's just a good practice for you for your test taking ability, which needs to get better as you go through because you have to take the MCAT or the, I don't know, whatever it is that you'll, PCAT or whatever it is that you'll take when you go on to your various pharmacy school. All right, or the GRE or whatever, okay? So it's useful practice to think about that now. You're not that far from that. In fact, you should be taking the MCAT this summer, frankly. You'll know that, right? Like your summer of your sophomore year? MCAT, that's what you should be shooting for. Am I right? Am I right? The other people told you all that? Ask Dr. Rowisher, she'll say sophomore. She knows. Okay, moment of inertia is which of these? All right, let's stop at 45. Okay, good. A is right. It's our rotational equivalent of mass. So where before we would have used M, now we're using I. We'll come back to this one. Let's try this problem. I'll work through this example for you, and then you can do one next. I think we have a quicker question. We're now going to begin to apply Newton's second law to rotational systems. And this will be a good example of a test question that you'll have. It'll probably be actually in your exam a multi-part question where I ask you multiple things about the system. First, what is the net torque? Maybe I'll ask you what is the moment of inertia? What is the angular acceleration? And then I might ask you something about the velocity or the displacement. So here, first thing I want to ask here is I have this disk that's allowed to rotate about this axis. It has a mass of 1 kilogram, and I want to know its angular acceleration. I want to know what alpha is, and I want to know what omega is. I can write down some things that I know. I know that the mass is 1 kilogram. I know that the radius of this disk is 1 meter, and it has these forces acting on it. First thing I want to do is find out what is the moment of inertia. On these rotational problems, I always know I'm going to need the moment of inertia, so I might as well just go ahead and calculate it first. I look at my table. And ask myself, okay, which of these is it? Which of these is it? Is it the hoop, the cylinder, maybe one of the cylinders, the sphere, the rod? Which is this, the spinning disc? It's this one, right? I told you that. Did I write it on there, actually? Oh, I did. So, yeah, it's going to be that 1/2 mr squared. A spinning disc is just like a flat cylinder. So that's going to be I equal 1/2 mr squared. It's going to be 1/2 my mass, which is 1 kilogram, times the radius squared, which is 1 meter. Square it. So that's equal to 1/2 kilogram meter squared. Okay? I'm going to tuck that away and I'll sort of save it and use it later. The next thing that I want to do is I want to find my net torque. We've done this before, right, with the rods. So my net torque is going to be equal to torque 1 and torque 2. I'll call this torque 2, this torque 1. I need to figure out the signs for each. Is torque 1 causing clockwise or counterclockwise motion? Counterclockwise, because this force is making it go in this direction. So this torque is positive or negative? Positive. Counterclockwise torques are positive. This force is causing clockwise or counterclockwise? Clockwise. Think of a steering wheel, right? That if I push up on this side, it makes it go in this direction, whereas this one makes it go in that direction. So, torque 2 is negative, torque 1 is positive. Positive torque 1 minus torque 2. That's my sum of my torques. That's going to be, remember that torque is equal to Fr sine theta. In this case, theta is 90 degrees for both. It's perpendicular to the moment arm, and sine of 90 is 1. So it's just going to be Fr times Fr. So 1 Newton times 1 meter minus 2 newtons times 1 meter. That's going to be negative 1 Newton meter. So the net torque is 1 Newton meter in the clockwise direction. Now the next thing I want to do is find the angular acceleration. So as we're doing steps, you can think of this is my first step, this is my second step. To find alpha, I say torque is equal to I times alpha. That's negative 1 Newton meters is equal to 1/2 times alpha. So alpha then is equal to negative 2 radians per second squared. And then I also wanted to know what is the velocity after 3 seconds. So I might ask you an additional kinematics question. To find that angular velocity, it's omega naught plus alpha t. Omega naught, it's initially at rest, so that's 0. And so this is equal to negative 2 radians per second squared times 3 seconds, just 6 radians per second. Negative 6. It's a good example of a test question. We'll certainly work some examples as we move along, but you'll see a question like this where you have to go through these processes. It's a lot like what we've done before. Really the only thing that's new is our moment of inertia, calculating the moment of inertia, okay? And the net torque, which we've already saw. We saw that before the exam. But it sort of brings stuff together. I'm going to hand back your exam, so we'll call it quits there. Guys, registration is this week. We have plenty of spots in the lab. And sometimes the lab, the section that you want particularly, fills up quickly. So register as soon as you can. All right? You understand? And then we also have a 3M and a 4M section. I don't know which one will be more popular, but I think the 4M will probably be more popular. So if you're able to do a 3M and lots, please do so. I'd love to have a smaller class so we can do sort of more personalized practice in class. Come on in here, I'll just call up and then you can come up and grab your test, and then you can go. Actually, hold on. This is good.